What is the pH of a 1 liter buffer made with 0.400 moles of HF? The Ka of HF is 6.8 times 10 to the negative 4, and 0.300 moles of NaF, to which 0.200 moles of NaOH were added. Okay, so in this problem, we are given a buffer. And the buffer contains two things. Number one, it contains HF. And we know that HF is hydrofluoric acid. It's a weak acid. The buffer also contains F minus, or the fluoride anion. So you may be wondering, where does F minus come from? It comes from NaF. So remember NaF, or sodium fluoride, when you put it in water, it's a strong electrolyte. It will dissociate into its two ions, the sodium cation and the fluoride anion. So this is where we got F minus. So F minus is the conjugate base of HF. Okay, and the problem says you added NaOH to the buffer. And what do we know about NaOH? NaOH is a strong base. So when you add the strong base to the buffer, which component of the buffer will react with the strong base? Obviously, it's the HF. Remember, the acid reacts to the base. So when you put NaOH into the buffer, the NaOH, a strong base, will react with HF, an acid. Okay, so you need to write the reaction between HF and NaOH. So HF plus NaOH. Remember, when you react an acid and a base, the products are, we have the salt, NaF, sodium fluoride, plus water. Okay. Now, after writing the reaction, let's write their initial amounts, initial moles. So in the problem, it says here, the initial amount of HF is 0.400 moles. For NaOH, it's 0.200 moles. For NaF, the initial amount is 0.300 moles. Let's not mind water. Although water is a product, we're not concerned about water. Okay, so let's just put water. Let's just set aside water. Okay, so those are the initial amounts. Let's move on to the change. So look at the left side of the reaction. So we have HF 0.400 moles and NaOH 0.200 moles. So obviously NaOH is the limiting reactant. So NaOH will get consumed completely. So NaOH will get consumed completely. So you put minus 0.200 moles for NaOH. Of course, also put minus 0.200 moles on HF because HF and NaOH reacts together. And then for the product, you put plus 0.200 moles. Why plus? Because the product is forming. Okay, now let's get the final moles. So for HF, 0.400 minus 0.200, that's 0.200 moles. For NaOH, 0.200 minus 0.200, that's 0 moles. For NaF, 0.300 plus 0.200, that is 0.500 moles. Okay, now that we have the moles of HF and NaF, so we got 0.200 and 0.500, we can now get their concentrations. So first, let's get the concentration of HF. Remember, how do we solve for molarity? That's moles per liter. So we have 0.200 moles of HF divided by, in the problem we are given 1 liter of the buffer. So divided by 1 liter. So the concentration of HF is 0.200 molar. For NaF or F minus, we have 0.500 moles divided by 1 liter, that's 0.500 molar. Okay, so now that we have the concentrations, we can now solve the pH of the buffer. And there's one formula we use to solve the pH of a buffer. That's the Henderson-Hasselbalch equation. So if you can recall, the formula is pH is equal to pKa plus log concentration of the conjugate base, which is F minus, divided by the concentration of the weak acid, which is HF. And we know that pKa is equal to negative log of the Ka. So if you want to solve for pH, pH is negative log of the Ka, which is given to us in the problem, 6.8 times 10 to the negative 4 plus log the concentration of F minus is 0.500 molar divided by the concentration of HF is 0.200 molar. So grab your calculator and type this entire equation. So negative log 6.8 times 10 to the negative 4 plus log of 0.500 divided by 0.200, and you will get a pH of approximately 3.57. So the answer to this question, the pH is 3.57.